In the previous lectures, we saw what is Laplace transform, how we obtain Laplace transform from Fourier transform just by multiplying any given signal if it is unstable with a decaying exponential, and then finding the Fourier transform of that signal gives us the Laplace transform. So basically, Laplace transform is derived from Fourier transform in our analysis. So once we obtain the Laplace transform, then we have several properties just like how we had in the Fourier transform. So basically, we say the Laplace transform exists whenever the Fourier transform exists for the signal x of t e power minus sigma t, right? So where does this Fourier transform exist? For what all values of sigma does this Fourier transform exist? So those set of values are what gives us the ROC, which is basically the region over the S plane. The S plane is nothing but the sigma and j omega put together is what we refer to as the S plane. So the ROC keeps changing whenever some changes are made to the signal. So when we try to understand the properties of Laplace transform, we need to also understand what happens to the ROC. And in particular, we also said that if the Laplace transform is in the form of a rational function, which means the Laplace transform can be expressed as some polynomial divided by another polynomial. So if it is in the form of a rational function, then it has another nice representations. We can use the pole zero plot representation to completely understand the system. So pole zeros also, we saw that if we just were given a pole zero plot, we can understand if it is an high pass system or a low pass system, and from Bode plot we can completely understand what happens to the frequency response, and we can also do the design operation from the Bode plot. Somebody gives you the Bode plot, from there you can design the corresponding system. So if the Laplace transform is a rational expression, then a lot of nice properties come into picture and a lot of usefulness are there for such systems. Now what happens to these Laplace transform when we make certain change? Now let's see some properties of this Laplace transform. So we also need to understand what happens to these poles and zeros when we make some changes to the time domain signal or to the Laplace transform of a signal. So the properties of Laplace transform will now include both the changes that occur to the ROC or the pole zero plots. So the first property that we'll see, just like the case of Fourier transform and the Fourier series, is the conjugation. So what happens when you conjugate in the time domain? The Laplace transform, how does it change? So we know that the Laplace transform is computed in this fashion: e power minus st dt, and the inverse Laplace transform is computed as 1 by 2 pi j integral Now, the first property that we are trying to see is, what if we take the conjugate of x star and then apply the Laplace transform? So, if we apply the Laplace transform on the conjugate of x, you can take this conjugate outside just like what we did in the Fourier transform. So, you take this conjugate outside, which means you have to apply the conjugation operation here. So how do you apply conjugation operation to this particular expression? So e power minus st is nothing but e power minus sigma plus j omega t. So in other words, you can say that this is minus sigma t multiplied with power minus j omega t, the whole conjugate. Now this term is purely real. This is real. This is the only complex part. This is complex. So the conjugation is going to affect only this part. In other words, this becomes e power plus j omega t. Okay. So which is equal to, this is equal to e power minus s star of t. Why is that? Because s is equal to sigma plus j omega, and S star is equal to sigma minus j omega, and minus S star is minus sigma plus j omega, and that's what we have here. So in other words, this is equal to so let us say some V is equal to S star. So then we have minus Vt dt the whole star. So this is nothing but Laplace transform of x. So this expression is exactly Laplace transform of x with the conjugate. So this is x star of v, and substituting v, we get x star of s star. So what this tells us is, if you take the conjugation of the signal in the time domain, then in the Laplace domain, not only does the Laplace transform get conjugated, but the s value also gets conjugated. In other words, if you have the s plane, then the magnitude here, why does the magnitude not change? Because the conjugation operation is not going to change the magnitude. So there is an s star, which means the negative values of omega comes in the positive value, and the positive values of the omega come on the negative side. So there is a flip about the x-axis. So if previously there was an ROC which looked like this, it is now flipped about the x-axis. But because it is anyway flipped about the x-axis and the ROC extends from minus infinity to plus infinity in the y direction, it does not make a difference. So the ROC remains the same. So if x of s, the Laplace transform of x of t, converged in this region, then the Laplace transform of the conjugate will also continue to converge in the same region. And intuitively this is true, because what are we saying? We are simply saying that x of t times e power minus sigma t, the Fourier transform of this signal exists. That's what we are saying in this region, in this ROC. Then it obviously means that this is absolutely integrable inside a particular ROC. And if you take its conjugate, obviously the conjugation does not change the magnitude, which means x star of t times e power minus sigma t, which gives the same magnitude as x of t e power minus sigma t, should also be absolutely integrable. So this tells us that the ROC should not change. So intuitively we can see from here that the magnitude is not changing, because of which the ROC should also not change, and that's exactly what is happening. There is a flip, but that does not change the ROC, because the flip is about the x-axis. Now the actual value of the Laplace transform itself, there is a conjugation operation, but that does not reflect in the S-plane plot, because in this plot we are plotting only the magnitude. So when we plot the pole zeros, then we see a difference. So let us say now we are plotting the location of poles and zeros, and let us say there was a pole like this and there was a zero like this. Now for real values, nothing changes. Okay. So because the conjugation operation does not affect the real values. Now if something was complex, okay. Now let us say that we have a zero or a pole which looked like 1 by s plus a. So let's say this was our Laplace transform. Now the new Laplace transform will look like x star of s star, which is 1 by s plus a, replace this s with star, and then there is a whole star. Now bringing this conjugation that is outside into the term that is inside, so you get s plus a the whole star. This is nothing but s plus a star. So then this tells us that the poles now will flip, meaning if there was a pole that was present here, let us say this was a plus jb, then after this conjugation operation, that shifts here to a minus jb. So if the pole and zeros are real, then they are not affected by this conjugation operation. But if they are complex, then they just are reflected about the x-axis because of the conjugation operation. And that's what we have here. Now, what if we just do a time reversal? So the time reversal intuitively should not affect the absolute integrability of the signal. So let us see what happens when we do a time reversal. Do a time reversal. We're trying to find out the Laplace transform of x of minus t e power minus st dt. So simple substitution, we'll say v equals minus t. So because of which this becomes integral minus infinity to infinity x of v e power sv dv. We'll get dv equals minus dt. There is a minus sign here, but there is also a change of the limits, so they cancel out one another. So this is what we get. So what is this? This is nothing but x of minus s, right? So we can just simply say that you can say s is equal to some minus another change of variable. Let us call this variable as some w. So we can rewrite this as integral x of v e power minus wv dv, which is x of w. So but w we know that is x minus s. So just by change of these variables, we get that this is x of minus s. So whenever there is a time reversal, there is also the s domain reversal for the Laplace transform. So what does this imply for the ROCs and the pole zero plots? So intuitively, we would expect nothing to happen to the ROC. Why is that? Because if x of t is absolutely integrable, then x of minus t should also be absolutely integrable, right? But the catch here is that we are looking for the absolute integrability of x of t e power minus sigma t. So how does e power minus sigma t look like? The e power minus sigma t is a decaying exponential for positive values of time. But as time becomes negative, it's an growing exponential. So if you reverse x of t, so let us say the x of t looked something like this. Now x of t times e power minus sigma t will become an absolutely integrable signal because this growing part here is cancelled out by this decaying part, and the same here. But when we time reverse x of t, we get x of minus t times e power minus sigma t. Now the x of t is a growing. Now e power minus sigma t is the same exponential which decays for positive values of time and negative values of time, it grows. But what happens to x of minus t? Now x of minus t starts becoming a growing signal for the negative values of time and a decaying signal for the positive values of time. So if we multiply these two and try to find out what happens to their absolute value, it's not going to be absolutely integrable anymore because in this region, it's going to grow unbounded. So just by flipping the signal in time, what happens to the ROC? The ROC changes because the absolute integrability of the signal also changes. So what happens to the ROC now? Then the ROC flips. So what do I mean by that? So if the ROC earlier looked like, let us say, this region, now it will flip and get transformed to an ROC which looks like this. Why is that? This makes sense if you think about it because the properties of Laplace transform clearly told us how the ROCs will look like. If the signal is right-sided, then the ROC is also going to be right-sided. If the signal is left-sided, then the ROC is also going to be left-sided, right? And that's exactly what should happen when you take the time reversed signal also. When you take the time reversal of a right-sided signal, it will become a left-sided signal, and a left-sided signal will become right-sided when you time reverse, and that should get reflected in the ROC. So the ROC also flips direction when there is a time reversal. What happens to the pole zeros? So the pole zeros should also get affected equivalently, right? So it's very simple to analyze what happens to the poles. Let's take an example. So if this was the actual Laplace transform, then what happens to the Laplace transform after time reversal? It is minus s plus a, right? So now what has happened? Then the sign of the pole or zero has changed. So whatever was in the earlier case, we saw a reflection about the x-axis. Now we will see a reflection about the y-axis. So the sign changes, which means, let us say earlier if there was a pole that was present here, okay, so this is some a plus jb. Now the sign changes, because of which we will see a reflection about the origin. So we will get a pole that is present here. So similarly, if there was a 0 here, then the 0 comes here after reflection. So let's see the next property. The next property is about linearity. So linearity is once again very simple property. So if we add two signals, then the Laplace transform also get added. But the question is, what happens to the region of convergence? So if we have two signals, x1 and x2, then if you apply Laplace transform to them, you just find out Laplace transform of this whole superposition, then it is as good as just finding out their individual Laplace transforms and then superposing them, because nothing but a variant of the Fourier transform, right? So Fourier transform is anyway linear, so these properties will also carry over here. So the Laplace transform is also linear. But the important thing to note here is the region of convergence. So nothing happens when we do in the Fourier transform, nothing changes, the spectrum simply gets added up, so there is nothing to worry about. But here the region of convergence is something that we have to worry about. Why is that? Because so you have to note that Laplace transform of x1 of t also should exist and the Laplace transform of x2 of t also should exist. So in order to ensure that both of these Laplace transforms to exist, it can happen only when you pick values of s which are present in the ROC of x1 and the ROC of x2. So only when those values of s that are picked which are common between these two ROCs, we can ensure that the entire Laplace transform, which is the sum of these two, will exist. In other words, the ROC is now going to be the intersection of the first ROC and the second ROC. But there is an exception. So the exception is that if the sum becomes a finite length signal, both the poles multiply together. So the poles are now just getting summed up together. In other words, the poles are now a union of whatever was the previous pole. So whatever was the pole here for x1 will also remain as the pole for this summation. Whatever was the pole for x2 will also remain as a pole for this summation. And intuitively that is true, because what happens to the Laplace transform at the pole? The Laplace transform goes to infinity. So if one of the terms goes to infinity, then the summation will also go to infinity, right? So the poles will remain as such, but the zeros will change, because now here we have s minus a multiplied with s minus di plus something. So you have to refactorize this numerator to get the zeros. The zeros will be different, and that also intuitively makes sense, because if this term goes to 0, there is a second term here in the summation that may not go to 0, right? So the zeros will change, whereas the poles will get added up together. Now let's try to see what happens when there is a time shift. So we compute the Laplace transform of x of t minus some b e power minus st dt. So we'll do as usual what we used to do earlier. We'll just do a change a variable. So let us call some alpha equals t minus v, then minus infinity to plus infinity x of alpha e power minus s alpha plus v d alpha. So this is nothing but e power minus sv, because v is constant with respect to alpha, and this integration is with respect to alpha. So this is x alpha e power minus s alpha plus v d alpha. This entire thing is now e power minus s v x of s. So whenever there is a shift in time, what are we saying? So we are seeing a multiplication by an exponential in the Laplace domain. So intuitively, if you think about what happens to the ROC, if x of t e power minus sigma t is absolutely integrable, then its time shifted version should also be absolutely integrable, right? So if the Laplace transform exists, then we say that this quantity is absolutely integrable. This quantity is absolutely integrable. But just by shifting in time, we are not changing the absolute integrability here, right? Because it's the same signal and the area does not change. Shifting in time does not change area, and it is also not flipping the direction. So because of which the values of time that we are concerned about here is still in either right sided or left sided, or it remains the same side. So the side does not change and the area also does not change. For this reason, shifting in time does not change the absolute integrability of the signal, and hence the ROC remains the same. There is no change in ROC. So no change in ROC. What happens to the pole 0 plots? So let us say that we had x of s to have some zeros and some poles. Now what happens to the pole 0 plot when you multiply with an exponent like this? First of all, now it becomes trickier to talk about the pole 0 plots because this expression is not rational anymore. X of s can be rational, but the time shifted version's Laplace transform is not rational anymore. Okay, so it becomes difficult to talk about the pole 0 plot for this expression. So it's not as straightforward as earlier. So let's do the other way around. So what if we do a shifting in the Laplace domain? So let's see what happens if we shift in the Laplace domain. So in the Laplace transform equation, let us say that we'll replace this s with s minus v. So we get x of s minus v is equal to integral x of t e power minus s minus v t dt. So this is equal to integral x of t e power vt e power minus st dt. In other words, this is the Laplace transform of x of t e power vt. So when you shift it in the Laplace transform domain by some quantity, the corresponding time domain representation is just a multiplication with an exponent. But what happens to the region of convergence? So does it change? The region of convergence has to change because, so think about the case. So let us say that x of s has some region of convergence ROC, and let us say that x of s converged for some sigma which belonged to this ROC. So let us say for some sigma belong to this ROC, x of s exists. Okay. So when will this x of s minus v attain that sigma value? In other words, x of s minus v will also exist if s minus v, if the real part of s minus v is equal to sigma. You can pick any sigma value from this region of convergence, and the Laplace transform will exist as long as the real part of this s is equal to this sigma. So by the same argument, because s of s minus v is simply nothing but a shifted version of the same Laplace transform, that will also exist when the real part of S minus V is equal to sigma. In other words, the real part of S is equal to sigma plus the real part of V. So, if this belongs to the original ROC, then the new ROC of new is equal to the original ROC plus the real part of V. In other words, if we had an ROC something like this, after shifting it with minus V, what happens is we get a new ROC which is going to move if V is positive, if the real part of V is positive. And this makes sense because what is the shifting operation? The shifting operation is as good as moving things in the right side, right? So, in other words, if you had a signal which is evaluated over the S plane and you are shifting the S value by some minus V, it is shifting the entire thing to the right side. And that is exactly what is happening here, it moves to the right. If V was negative, then you get S plus V, then things would move on the left hand side. So, the new ROC is shifted by the amount which is equal to the real part of the shift here in the Laplace domain. And what happens to the poles and zeros? The poles and zeros simply also get shifted, right? This makes sense because you are shifting this entire thing. So, if we have a pole zero function which is given by this rational form for the original Laplace transform, wherever there is a S, we just replace that with S minus V, right? So, the new 0 would be V plus AI and V plus BI. So, the poles and zeros, you just simply shift them by the same amount that the Laplace transform was shifted. So, when you shift in the Laplace domain, in the time domain there is a multiplication with an exponential which results in the shift in the ROC and also a shift in the poles and zeros. Now, what if you scale in the time domain? Let us see what happens when you scale in the time domain. So, we compute Laplace transform of x of ct e power minus st dt. We'll do the same thing as always. Let us change the variable of integration. We change the variable of integration, the limits don't change. X of v e power minus s divided by dv equals c times dt. So, therefore, we get dv by c. Okay. So, this is equal to, so there is a mod c, because if there is a minus sign here, the limits of the integration also change and then there is a corresponding shift. So, you get 1 by mod c integral x of v e power minus s divided by c dv. So, this is nothing but the Laplace transform which is also now scaled by c. Okay. Now, what happens to the region of convergence? So, if a signal is multiplied with c, then essentially what are we doing? We are trying to either compress it or expand it. So, which means the energy changes. If the energy changes, then the absolute integrability should also change and hence there should be a change in ROC. So, what happens to the ROC? Do you think it expands or it decreases? It depends upon the value of c, right? So, if c is, let's say, greater than 1, if c is greater than 1, the signal actually shrinks. So, if the signal is actually shrinking, then you would expect it to have lesser energy. If it is lesser energy, then it should become absolutely integrable for more values of sigma, right? Because it has lesser energy, so it should be easier to make it absolutely integrable than earlier. So, the ROC should increase. So, ROC should expand for c which is greater than 1. And when c is less than 1, the energy decreases. If the energy, and when c is less than 1, the signal in time domain expands. So, if it expands, then the energy increases. If the energy increases, then you would take a higher valued exponential, that is the exponential with which you decay the signal should have a higher exponent. so that it now has absolutely integrable property. So you will require higher values of sigma now, which means the ROC has to become smaller, it has to shrink. So when C is less than 1, the ROC would shrink, because in the time domain the signal contains more energy, whereas when C is greater than 1, in the time domain the signal has lesser energy, so the ROC will also expand. But what happens to the poles and zeros? So as you can observe from here, all we are doing is just replacing S with C. In other words, if we had a pole which looked like this, now after this time domain shift, we have S by C here, which is now equal to 1 by S plus AC whole times 1 by C. Now this becomes a constant, so we can ignore that. So the pole and 0 just get multiplied with this constant C. So the poles and zeros also now change, they simply get scaled by the same amount. So that is what we have here. So whenever C is greater than 1, there is an expansion of the ROC, and wherever C is less than 1, there is a shrinkage in the ROC. So the entire ROC now is now scaled by this constant C. The poles are also scaled, the zeros are also scaled.